This is just a brief tutorial on flow scaling and the hydrostatic balance. We discussed in prior lecture the Navier-Stokes equations, which are the governing equations for the fluid. In here we've added rotation because we're working within the non-inertial earth rotating reference frame. So we have equations for continuity, expressing conservation of mass, and momentum in three different directions: u, the x direction, v momentum in the y direction, and I should say w momentum and the z direction. We have terms for the acceleration and advection of the fluid, the pressure gradient force, the fictitious Coriolis force, and diffusion of momentum, both in the horizontal with the coefficient of diffusivity AH, y, and in the vertical with a separate coefficient of diffusivity Km. The W momentum, so the vertical momentum equation, is this last equation here. It doesn't have the Coriolis term because it's small enough that we've already dropped it. So we have these diffusion terms, we have advection in our total derivative here, and acceleration, pressure gradient, and we have the gravitational acceleration here. We can scale this, these equations. We're going to start by scaling continuity. So I took a continuity equation, I rewrote it. I brought the partial w, partial z over to the left-hand side of the equation, equals minus du dx plus dv dy. And what we're going to do is evaluate the size, relative size of these terms, of the three different terms for a specific problem. In this case, we're thinking about the ocean basin. So we're going to scale each of these things, each of these items in here, distance scale and velocity scales, in order to determine a rough order of magnitude of the size of each of these terms. So for W velocity, we're going to scale it using some constant W velocity, and we're not quite sure what that is at the moment. The U and V velocities we will scale using a constant U velocity. The X direction we will scale using some constant L. And so we're thinking about, in terms of scaling, when we apply these constants, we're thinking about what are rough orders of magnitude for these values in our area of interest. So we're talking about ocean basin down here, and we're thinking about what are velocity scales, tens of centimeters per second. What's a length scale? About 1,000 kilometers or bigger. What's a depth scale? About 1,000 meters. So this is back of the envelope calculations. We're doing a rough estimate just to get a sense of the different size of these terms. By scaling our velocities, we can replace these terms here with our scaled quantities and get a sense of what the size of the scaled quantity is. So partial W, partial Z scales as W over H, and du dx and dv dy both scale as U over L. And so we see here that the scale of the W velocity, the vertical velocity, is equal to the horizontal velocity times this factor, which we call the aspect ratio, the ratio of depth in the ocean to the length scale of interest. So this gives the relation between the vertical and horizontal velocities. We see conservation of mass tells us it has this relationship here. For the ocean basin, we have 10 centimeters per second, and we are applying a length scale and a depth scale because we have some sense of those values. And this tells us that a typical vertical velocity is on the order of 10 to the minus 4 meters per second, or tenths of millimeters per second. So it's very small. You have tens of centimeters per second for the horizontal velocities, and you have tenths of millimeters per second for the vertical velocities. And this is because the ocean's like a sheet of paper, essentially constrains the motion to be in the horizontal and only allows for very small vertical motions, tiny vertical motions. Now this is not necessarily true everywhere. You can have places of stronger upwelling or bathymetric changes, but this is just to give a general order of magnitude, and that's what continuity tells us once we scale it. It tells us something about W at the scale of ocean basins. If we scale the W momentum equation, we can go through the same process. So we have our terms here, and we replace each of these with a quantity of an assumed size. So we have dw dt, the rate of change of our scaled vertical velocity scale divided by our time scale, or horizontal velocity times our vertical velocity scale divided by our length scale, etc., etc. We don't really know what to do with the pressure gradient. Gravity, we know what that is. We have a number for that. And then we get to our diffusion terms. You see they're of dimension, velocity scale divided by length scale squared. So there you have your W over L squared as a characteristic size. For the characteristic velocity and length scales gives us a scopes out the sense of magnitude of this variable times the diffusivity. So for diffusivity, we're just going to plug in a value. We can make some scaling arguments about that, but we won't go into that here. We're going to plug in a rough value for that, and we come up with our sense of what these are. So we're going to use 10 centimeters per second for U, and the length scale again be 1,000 kilometers, and G we know is 10 meters per second squared, and the density is 1,000 kilogram per meter cubed. Depth is roughly 1,000 meters. We got our velocity scale from the previous work on the continuity equation, and we're going to make this assumption about the horizontal diffusivity at this length scale being 10 to the 5 meters squared per second. Pressure gradient we'll leave alone, and we'll talk about time scales in the order of weeks. So this is not what's happening instantaneously over the course of years. We're thinking about changes that occur over weeks. If we plug those numbers in, we get, for rough sizes of the terms, 10 to the minus 10, 10 to the minus 11, minus 11, minus 11, unknown, that's the pressure gradient, 10, which is our gravity, 10 to the minus 11, 10 to the minus 10, 11. So the sizes don't matter. It's the relative sizes that matter. These are separate terms making up the force balance in an equation, and you can see there are two terms. Well, there's one term that clearly is much larger than all the other, but one term can't stand alone because it has to be balanced, which implies this other term, the pressure gradient, must be of the same order of magnitude, or else there is no one to work against the gravity. These other terms, we can essentially, at the scale, we can essentially ignore these other terms. We're going to cross them out. They're very small. The only one, they're all 10 to the minus 11 except for the acceleration, which is one order of magnitude larger, 10 to the minus 10, but it's nowhere near the orders of magnitude of the pressure gradient and gravity. So this is a parcel in terms of controlling the vertical velocity in the fluid. What's leading to the acceleration of that fluid in the vertical, you have the set of forces, but there are two of them that are so much stronger than the others, we can essentially ignore the others at these scales. So what does that lead us to? We cross out all the terms, we're left with just these two, and we balance this as an equation, it should be an equal sign, and then bring the density over the other side, and we have this simple equation here. Now if we integrate this equation, we get P, G is constant, pull G out of the integral, or solve for this differential equation here. The integral from minus Z, so some depth in the water column. So here's our water surface, here's our mean depth, and that's where Z equals 0. Here's our Z coordinate. This is the free surface height, which is eta in meters. And at some point in the fluid down here, at some point negative Z, that's where we want to know what the pressure is. This right here tells us what the pressure is at that point. We have an equation for the pressure. This is just our hydrostatic equation. That's all it is. It's a hydrostatic approximation. It tells us the pressure at any point in the fluid is given only by the pressure coming from the weight of the fluid above that point, which we're integrating over the density field to get that. If the density is constant, we can pull it out of the integral, and we have equals G rho times, G rho times the depth of the water column above that point, which is equal to eta plus Z. So this is the hydrostatic pressure we've discussed earlier in the class. So I noted this P underscore H, PH, P little h for hydrostatic. So at these very large basin scales, the pressure can be considered to be hydrostatic. There are other sources of pressure variation in the fluid, but they are small and negligible compared to those that come from the gravity pushing down on the fluid. So this W momentum scaling lets us know that we can assume the pressure equals the hydrostatic pressure. This is called the hydrostatic assumption, and essentially we can use this as our W momentum equation. So this is very useful because prior to this we had equations for momentum, which are essentially velocity equations. We had other equations which we discussed briefly for the changes in temperature, changes in salinity. We had equations of state, which gives us density from salinity, temperature, and depth. And we had some other equations we discussed briefly that allow us to estimate the diffusivities in the ocean. Those are turbulence equations. But pressure is an unknown variable, and we had no way of determining pressure prognostically from the equations. By making the hydrostatic assumption, once we have the density field and the free surface height, we can determine instantly with a simple algebraic relation the the hydrostatic pressure anywhere in the fluid. It's an instantaneous, and all that comes on this assumption that that pressure comes only from hydrostatics, which is almost entirely true. And at these scales, it's a perfectly valid assumption.